All right, we're on to the third part of the quantum mechanics lecture, and we're going to be talking about the de Broglie wavelength. Now, we just covered that for photons, right? For photons, P equals h over lambda. Well, now we're just turning that around and saying, well, lambda then must be h over p. And what de Broglie proposed was that this equation, in fact, applied to particles, not just photons. They'd just been through this whole, photons are waves, and now suddenly photons begin to look like they behave like particles. Now de Broglie wades in and says, you know what? I think particles behave like waves too, if the situation is right. And it turns out he was in fact correct. So, why don't we notice it? Well, if you take a 3 kilogram bowling ball, and at any reasonable speed that you throw the thing down or roll the thing down the bowling alley, you find it has a de Broglie wavelength around 2 times 10 to the minus 35 meters. That's kind of tiny. That's kind of tiny compared to everything we go through. And if you remember when we talked about the door and sound versus light diffracting through a doorway, the reason sound diffracted through a doorway and we didn't notice light diffracting through a doorway is that the doorway was comparable to the size of the waves of the sound waves, but so much larger than the wavelength of light that we didn't notice the diffraction. Well, here we're talking about something with an itty bitty, teeny, tiny wavelength, right? We would never notice the bowling balls diffracting as they pass through a threshold, because their wavelength is so small compared to any threshold they would ever go through, right? I mean, it's so small compared to the bowling ball, so you can't make a double slit experiment with the slits apart on a distance that compares to this wavelength, because the bowling ball simply won't fit through the slits. However, you can do this with electrons, and you can see in this picture we have here, you can see the diffraction pattern of electrons coming through a hole in a screen. So we do this with electrons all the time, and in fact, electrons, the diffraction of electrons through lattices is one of the ways we scan material. So that was de Broglie's one main contribution, and then along came Heisenberg. So Heisenberg started working at what are the limits of our understanding. And he reasoned that, we couldn't really know anything more about the position of a particle than something comparable to its wavelength. And that in terms of momentum, since we don't know position all that well, we kind of don't know momentum any much better than that, so there's some limits to our knowledge of things. And what he finally got to was, after working through the mathematics, that the product of the uncertainty in momentum times our uncertainty in position was always at least as large as h over 2 pi, if not larger. What does that really mean? Well, from a measurement standpoint, it means if I know exactly where something is, then I know absolutely nothing about its momentum. All right, because the product of these two, if I know exactly where if I know exactly where something is, delta x is 0, and that would, that means delta p has to go to infinity so that their product is greater than h over 4 pi. Or if I know exactly the momentum of something, I lose all information about where it is. And it turns out this principle holds and is a fundamental piece of fundamental mystery around what really happens inside these limits. All right, because things in our models happen inside these limits, but we don't get to ever observe that. This same thing can be stated in terms of energy and time. So we can know exactly when something happened and nothing to know about how much energy it had, or exactly how much energy an event had, but nothing about when it happened. So these things are a balancing act whenever you're doing measurements in high energy physics, and you're always bumping it up against Heisenberg's uncertainty principle. All right, that's it for our quantum mechanics lectures, and I'll see you next time.